Greetings and welcome to another exciting lecture in geomorphology. We're back again today and we're coming up to a very important part of the course. We have been talking about hill slopes for over the past week, and now we're moving on and talking about another really important topic, and that is fluvial processes. So now we're going to be thinking about landscapes and parts of the landscape that are shaped by rivers. So the background behind me here to start off, we're looking at beautiful Berry Creek in Yellowstone National Park. And what we're going to be thinking about over the next several lectures is thinking about how this river right here shapes and erodes the landscape. What are the mechanisms for moving sediment in a river? How are channels created? What are the controls on channels? That's going to be our plan for the next several lectures. So let's go ahead and jump in here. And let's start by asking some basic questions as to why one might be interested in studying streams. Why are streams important? And particularly here in geomorphology, streams are very important. If we think about all of the superficial processes, remember in our first lecture we talked about the roughly 12-ish geomorphic or geologic processes that shape the surface of the earth. Well, rivers are probably the most dominant form of dominant process shaping the terrestrial landscape. So rivers are very important. They flood, they erode, and they sculpt the landscapes we see around us. So right here, single most important geomorphic agent when we look at the terrestrial landscape. Rivers move more than just water. Rivers move sediment, and during floods, they dump that sediment out on the floodplains. So because of that, we end up with very fertile soil deposit or soils that form in river deposits on the banks of rivers. So rivers are important for agriculture. And so because of that, they've become important pathways for commerce and trade as communities have developed along rivers because we can move goods up and down them. So again, that's my next point here. Oftentimes where a lot of people live are next to rivers, so we end up having to control rivers and control how they flood to keep people safe that live near these rivers. Also, we need water for lots and lots of activities associated with civil society, whether that's for drinking water, for car washes, for agriculture. And so Americans here, we use about 1 trillion liters per day of water, highlighting the importance of understanding rivers and the movement of water. Okay, another part of this that's really important and interesting to me is the topic of stream restoration. We've done a really good job over the past, I don't know, 100, 200, 300, depends where you put the cutoff. Take home point, we have done a really good job of messing up rivers and trashing rivers over the past several hundred years. And so what we've seen over the past several decades is an interest in how we restore rivers and return them to a more natural form and some more natural type of function. And so because of that, it's big business and big money thinking about how streams work so that we can restore streams. So here's some pictures here kind of showing this idea of stream restoration, right? That we will make modifications to the channel to try and make it a more natural environment. And so this is another thing I'm really interested in personally and thinking about. We have research that looks at some stream restoration projects here in the Walla Walla vicinity. And I think it's also a great place when you're thinking about careers in geology. River restoration is a big business, and people in different government agencies and private sector are employed in the business of stream restoration. So for that reason as well, I think stream restoration is a really great field to be in. Okay, so let's start here with some foundational concepts in thinking about fluvial landscapes. And the first one is one that we've defined before, but I need to define again, and that is discharge here. Discharge is an important control on the morphology of a stream. So if we want to look at this stream here from Yellowstone National Park, think about the way the channel looks, why there's a bar. See this bar kind of over here in the distance, a mid-channel bar. We've got a floodplain, and we've got fine-grained sediments in that floodplain, and the top of the floodplain there. When we think about kind of the morphology of a river, discharge is going to be a really important control on that morphology. And so discharge is the amount of volume moving in the river per unit time. And so discharge, oftentimes we think when we want to measure it, we take our area of the channel, So that would be the air, well, excuse me, let me say it the way this top slide here says it. We would take the width of the channel going kind of across here. We'd multiply that by the depth of the channel. So length times length, we're going to get a length squared. And then we'd multiply by u here, which is our water velocity. So water velocity here, and so that is going to be in length per time as well. We end up with length, length, length per time. Multiply all those together, and we end up with cubic length, so volume per time we use. So oftentimes you'll see rivers, we'll see velocity units of cubic meters per second, and SI units, or in the English system, cubic feet per second are very common ways we kind of quantify that discharge. Some other terms here, this ACS is the cross-sectional area of the channel, so it's the depth multiplied by the width. So when we think about discharge again, we can think about discharge as the cross-sectional area multiplied by the velocity, or the width, the depth, multiplied by the velocity. Okay, another important term here that I want to introduce is the wetted perimeter of the channel. And so perimeter, that's essentially the length that's wetted under here. So generally, when we think about the wetted perimeter, it's the width, so this width here, measured by 2 times the depth to get that channel. Added to 2 times the depth. We have depth on both sides, and then we add that to the width of the channel. So that would be your wetted perimeter. Okay, another important concept we have to understand and quantify when thinking about rivers is not just the amount of water in the river, but how that water in the river exerts a force on the bed of the channel, and we call that shear stress. So here's our equation for shear stress. This should be kind of an old hat for you now after looking at free body diagrams associated with the infinite slope model. And so shear stress, what we're looking at here is this is just going to be essentially the force of the water on the bed of the channel. And so that shear stress tau is going to be equal to the density of water times gravity times the depth of flow times slope. So all of those are going to be important, quantifying that shear stress at the base of the river, which is going to be super important when we want to think about if our river, as we start the flood, if it's going to have enough stresses that entrain the bed and start moving the bed of the river during a flooding event. All right, another important part of rivers here, that would be right here. This would be thinking about the velocity profile with depth. So this is kind of a characteristic river profile flowing down, flowing downstream. There we go, flowing downstream, where what we see is that we have the fastest flowing water at the surface, and then we get decreasing velocity all the way down to the bed of the channel where we have the lowest velocity. Why is the lowest velocity at the base of the channel? Think about that. Why would that be? Yeah, you got it. Nice job. It's because of the frictional forces of the water interacting with the bed of the channel slows down the water at the base of the channel. So generally, because of this curve that we see, if we want the average flow velocity, it's about 60% of the depth, 0.6 of the way down our depth here. So if you're measuring the flow velocity, you want to get an average of not just what's happening at the surface, but the whole river profile. We go down to about 0.6. So that's important to think about. All right. So when thinking about those shear stresses then, how can we increase the shear stress on the bed? So we can entrain sediment. Well, there's 2 ways. The first is you increase the weight of water. You increase the weight of water, the depth of water, which is increasing that weight. You'll have more essentially mass that's pushing on the bed. So here we've got shear stress that's going to be increasing with our water depth. And at some point you'll exceed the strength of the material. You'll entrain that grain and start moving that grain. We'll talk about that more in our next lecture on sediment transport. Another way you could increase shear stress is by increasing that slope. So if we put this on a steeper slope, then you're going to have greater shear stresses. Essentially, you've got less frictional forces. Well, we're going to have less. Let me just say that as we increase the slope, we're going to increase that shear stress. And so the steeper the bed, the more likely you are to sediment. Okay. Next kind of foundational term, now that we've introduced some basics here, kind of discharge, shear stress, water velocity, is thinking about the variety of channel morphology that we see around the globe. There's all sorts of different types of channels. We see some channels that have a single, here we go, a single thread to them. So here's the Ohio River. So a single big channel, and then a slightly smaller river here. Here would be the Yellowstone River, just a single channel. But then if we look at rivers in Central Asia, look at this. We have multiple flow pathways as it looks like the river's kind of flowing across this unstable surface, right? There's no vegetation on this here. So we call this a braided channel. So here we're looking at different flow patterns, but if we were looking around the year, these types of channels would always be filled with water. And so because of that, we call these perennial channels. So these would be perennial channels. By that, we mean water's flowing with them in them all the time. The opposite of that would be an ephemeral channel. An ephemeral channel, generally in dry regions, this is where we have water that's only flowing when it rains. So here's an ephemeral channel in the Chihuahuan Desert. So this is some field work I was on back in grad school, helping a friend study some paleoclimate down here, and we're crossing these ephemeral channels. Got to be careful. They can still be a little wet in the mud, and you don't want to get your truck stuck in the mud. Here are some ephemeral channels on a flat alluvial surface out in the Mojave Desert. And so these channels here are only active when there is water flowing. Okay, the other big broad differentiation we make in rivers is rivers that are flowing in their own sediments. We'll call those alluvial channels. And then rivers that are flowing mostly on just bedrock, that there isn't much river sediment, and we'll call those bedrock channels. So generally we see in more mountainous terrain bedrock, and then in flatter terrain is with lower slopes is where we see alluvial channels. Okay, moving on then. Let's think about the controls on that channel and stream morphology. One of the most important controls on that morphology is going to be thinking about the input of sediment on the channel. So always remember that streams move more than just water, they move sediment too. And so we'll have like a rainstorm event, and so we are dumping water into the river as it runs off the landscape during overland flow. Remember that from geomorphic hydrology? Excellent. But also that overland flow is going to have shear stress, and so it's going to entrain sediment into it and dump that right there into that channel right there. So it's going to entrain the sediment here, pick it up, and drop it right there in the water. So we're entraining sediment in the water on the slopes and dumping it in. So streams carry more than just water. Okay, so here's an example of that. What we're looking at here is what looks like a really nice kind of clear water, but that's not always the case. This is the Gallatin River in Yellowstone National Park. And all these sediments on the side here, these are big debris flow deposits that have been dumped off in the channel. And so sometimes there's lots and lots of sediment that's being dumped into the channel. The channel banks themselves will provide sediment to the channel. So here we're looking at a rotational slump right here. And that slump is dumping kind of fine-grained sediment into the channel. And here we've got just the banks of an unconsolidated river. This is where we have steep banked rivers, arid regions where we have lots of aggradation of fine-grained sediments. We generally call these arroyos. And then all of this unconsolidated alluvial sediment, when we have a bank erosion, can be dumped down into the channel. Boy, another important thing to remember is that streams not only carry water, not only do they carry sediment, but yes, they always, not always, but they also are movers of vegetation as well. And so we need to make sure we are thinking also about how vegetation is influencing channel morphology and the movement of sediment and movement of vegetation down channel. So this is really important. Here we're looking at a log jam. So here's some trees that have fallen down, and then they're creating heterogeneity in the flow where we have some pools here and a pool above it. Here we're looking at flood debris that's been tangled up on this big tree mass right here. So this is very important. In fact, when we think about, when we start thinking about stream restoration, one thing we've recognized that one of the biggest changes between rivers now and rivers 100 to 200 years ago is that they don't have any vegetation in them. We've removed a lot of the vegetation. And one way we've done that is by the removal of things like beaver dams. So here is sediment that's been, here is vegetation that's been kind of stacked up in the channel, creating a beaver pond. So we have to think about that as well. On a little bit now, we've kind of identified different shapes of channels, channel morphology. What I want to do with that now is start thinking about how we can quantify fluvial processes, quantify like discharge and velocity and shear stresses. So the first thing we need to think about is that flow velocity. So we introduced this flow velocity here with about 60% down through the water column being our average velocity, lower at the base, higher up above. And if we think about that in a cross-sectional form, remember we said friction is what's driving this. So along the whole channel is where we're going to have friction. So we often see the slowest moving water. These are velocity contours here along the margins. The fastest moving water right in the center at the top of the flow. So how do we quantify that velocity? Well, one of the easiest ways to do it is one of these things right here. See this little propeller right here. Basically, this propeller spins around. You stick it down in the water. The force of the water is moving it. That propeller is calibrated, and we can tell us how quickly the water is moving by. Is it 1 meter per second? Or is it 1/10 of a meter per second? Okay, so a current meter is how we do this. Here's an example of someone using a current meter. So you stick it in the flow here. You can stick it at right here, 60% depth. Pop that thing down in at the right depth, and then you can measure that flow velocity. Okay, that works if you're around at the time you want to measure the velocity of flow. However, oftentimes we're interested in velocities associated with flooding events because that's when erosion is going to happen. More on that in a second. And so because of that, we need a way to characterize and quantify the velocity when we might not be there measuring ourselves. So for that, we use what's called Manning's equation. Manning's equation is a way for us to estimate the velocity of flow based on a few factors. So what these factors are going to be R, S, and N. So our flow velocity, according to Manning's equation, is equal to R raised to the 2/3, where R is the hydraulic radius. I'll define this in a second. S, which is slope, how steep that channel is. And then finally here our N, which is our Manning's roughness coefficient. So Manning's N is, we generally would just call roughness. And what that means is how rough is the channel. So think about this here. Think where this roughness term is relative to our velocity term, right? It's in the denominator on the other side of the equation. So if nothing else changes and our roughness increases, if roughness goes up, what must happen to our velocity? Right, because it's in the denominator, our velocity must go down if roughness goes up, right? Because it's in the denominator. And intuitively that makes sense, right? Imagine you've got a channel with a bunch of boulders sticking in it or a bunch of grass sticking in it. All that, the water is going to slow down as when it hits these frictional forces on the channel. And so roughness makes the water flow slower. And that makes sense now that slope's in the top, right? In the numerator. If we have steeper slope, the water is going to be moving faster. Excellent. Okay, so the other one that seemed a little bit more unusual, what is this R, this hydraulic radius? We define the hydraulic radius as the cross-sectional area of the flow, ACS, divided by the wetted perimeter. So cross-sectional area is that width times depth, and our wetted perimeter is width plus 2 times the depth. So hydraulic radius is our cross-sectional area, ACS. See if I can draw on. So if we want to do this again, R is now equal to ACS divided by WP. ACS divided by WP. That is our hydraulic radius. All right, what about that channel roughness? That's our next one. I've got some examples here, some channels for you. This bottom picture here, this is a channel in Erie, Pennsylvania, a bedrock channel. And just look at this channel. This is a channel with a river flowing in essentially siltstones and shales. And there's almost no vegetation along the base of the channel. There's almost no boulders. And so this looks very flat, right? And so this would have a very low roughness. Water would flow over it quickly compared to a channel choked in vegetation here, or a channel here like in Yellowstone with big boulders. So Manning's N is channel roughness, and it doesn't have a dimension, no dimension. And again, we generally just estimate these based on pictures. Here's a picture from your textbook of Indian Fork near New Cumberland, Ohio. Here we have, this is a straight canal with earthen banks, and so we'd estimate that Manning's N somewhere between 0.02 and 3. Rougher river here, this would be the West Fork of the Bitterroot in Montana. So this is the sand and gravel river with that, there we go, roughness of 0.03 to 0.5. Here would be an even rougher channel. This is in Washington. Kind of look at kind of this channel, lots of vegetation on the sides. This might have a Manning's roughness with a cobble boulder bed somewhere in 0.04 to 0.08. Here's another picture here of some cobble boulders, 0.04 to 0.08 as well. Okay, so that's Manning's equation. Why do we need Manning's equation when you can just stick a flow meter in the flow? Remember? Because you're not always there with a flow meter. What if that flood happened 10 years ago and you've got a high water mark so that you can estimate the cross-sectional area? Then you're going to need Manning's N to measure that velocity. All right, great job. Whew. All right, another really important number used to describe flow, and it's going to change the types of bed forms we see, which we'll be talking about, is what we call Froude's number. Froude number is a way that we basically think about flow from being either a tranquil flow, which our Froude number is less than 1, to rapid flow, which is Froude numbers greater than 1. And critical flow is right at that boundary. So to define the Froude number, it's going to be equal to our velocity divided by our depth of flow and gravity raised to the 1/2, 0.5. So that's how we determine the Froude number. And you've seen examples of the Froude number kind of in the changes from tranquil to rapid flow in lots of places. So one of my favorite is in the sink. And so as the water comes down, this is fun, I'm done. Woo! Water goes all the way down, boom, there, it hits there, and it starts to spread out. And as the water spreads out, it spreads out in all directions. Hold on, let me get my pen out here. So the water spreads out in all directions. And so because of that, the water is moving over a larger and larger area as it spreads out. And so what happens is that velocity goes from high to low. And so we lower this number and we go from rapid flow to tranquil flow. And so right here, we're in the rapid flow, and then we move out to the tranquil flow. And right where we have that change, where we have critical, we end up developing what's called a standing wave. So standing waves happen where we have basically water that's hovering right around that rapid to tranquil flow. Another place we see standing waves is along rough water. And so you might have seen these before. Kayakers love these, right? Here's a standing wave right here. And this is where water is moving down. And right here, we're moving from rapid to tranquil flow. And as we do that, we change kind of our flow characteristics. This is also known as a hydraulic jump. Yep, a hydraulic jump. So boaters get really excited by these as you're boating. And so where you get hydraulic jumps, oftentimes it's where that velocity is changing really quickly. That velocity is changing because we end up seeing changes in the depth of flow. So this is what happens in channels, not in your sink. So here what we're looking at, does everyone see this little bit of quick water right here? It looks like it's moving really fast. That is right here. And notice we've got some big boulders. See these boulders on both sides of the channel right here? You can see some boulders underneath the channel, underneath the water as well. Does everyone see that? Was I covering up what I was writing on? Yep, sorry about that. So that's what I was writing on. We got boulders here, and you can even see the boulders in the channel on the other side. This is a debris flow deposit in this channel. And what's happened is that in the location of the debris flow, we've increased the velocity of the water. So the water velocity goes up, and we're increasing our Froude number, and we're moving into rapid flow. As we get on the other side of the debris flow, we end up thickening our water again as we move over the impediment. The water then has to slow down, and we develop a standing wave. Excellent. Okay. So here, above our boulders, we have Froude numbers less than 1. So this is that subcritical flow. And then as we move on to the boulders, so here our depth is decreasing. We end up with that supercritical flow. And then right at that boundary, as the water starts to thicken again, we end up with fluctuating flow going back down the subcritical flow with at that supercritical subcritical boundary, which is equal to 1. So if I were to draw this here, if I just draw right here, here's our channel. Then here's the bed right here with the big boulders in it. So on this side of the boulders, our depth goes up. Because of that, our velocity goes down. As we move onto the boulders, our velocity has to go up because that water still has to go through there. It can't get stacked up behind. The water behind it is pushing it down. And so here, our depth decreases, and as depth decreases, that velocity has to go up. Oh, we lost our picture. Let me get that back. All right, we're back. And then finally, when we hop to the other side, and right here is when we go back as we develop those hydraulic jumps. So here's a nice picture of a hydraulic jump as we're transitioning at that critical flow. Excellent. So going back all the way here to our Froude number then, some other terms I was using is subcritical, and then supercritical, where Froude numbers are greater than 1. And critical, right, where Froude numbers. Okay, great. There's that hydraulic jump again. Okay, now that we've able to define kind of our flow a little bit more quantitatively, I want to talk about another important term, and that's what we call effective discharge. So effective discharge is the discharge that moves on average the most sediment in the river. And so this might not necessarily be the biggest flood, because the biggest flood might not happen that often. But it's not necessarily the smallest either, because the smallest flood might not have enough shear stress to move that much sediment. The effective flood is the discharge that transports the most sediment over years to decades. And this is really important because we often think about the effective discharge as controlling the morphology of the channel. The form of the channel is related to that effective discharge. And so here we go, thinking about discharge on our x-axis here. And so big discharge here, so big floods over here. Then on the other side is not so big floods. And so here, this is the frequency of events. So we have more often smaller floods and very few of these big floods. But this is our what we call our sediment discharge rating curve. This is how much sediment we can move in our floods right here. And so up here, these are the really big floods, but they just don't happen that often. So our effective discharge is essentially kind of the product of magnitude and frequency. And that's going to be the flood that moves the most sediment on kind of the time scale of decades. And so because of that, because of an effective discharge, rivers tend to be have a typical morphology associated with their flow conditions. And we call that hydraulic geometry. And so hydraulic geometry tells us that the depth of flow, the width of flow, and the velocity of flow are going to be proportional to discharge. That's because discharges are effective of moving that. And so what we generally see is that by the concept of hydraulic geometry, the width, the depth, and the velocity are going to be equal to changes in discharge. So the greater the discharge, the greater the width. The greater the discharge, the greater the depth, and the greater the discharge, the greater the velocity. Our A, C, and B are our A, C, and K, and our B, F, M are exponents. Are the exponents and the factors that kind of vary depending on your channel and where you are. So that's the way we can fine tune this equation to a particular river. But our A, C, and K's are empirically derived constants, and then our B, F, and M's are empirically derived exponents. Q is that discharge. So again, in the field, depending on what river you are, we can solve for these B's and Q's, and what we're going to be measuring is our discharges and our widths. So what this tells us then is that according to hydraulic geometry, as discharge increases, so does the channel width, so the width of this channel. As discharge increases, so does our channel depth. And finally, as discharge increases, so does our water velocity. So that's the concept of hydraulic geometry. And our lab this week is going to be quantifying discharge and potentially hydraulic geometry. Okay, so one of the remaining couple of terms I wanted to discuss here, moving on from hydraulic geometry, a very important term is stream power, and that's the potential for flowing water to do geomorphic work on the channel. So we often talk about the power of flow, and so this is our stream power term right here. So that's stream power, and that's going to be equal to the density of water times gravity times discharge times slope. Now, oftentimes we're interested in the power per unit area of the channel, so we actually define instead unit stream power. And so unit stream power is just that total stream power divided by the width of the channel. That allows us to think about the erosive potential along the channel. Okay, so an interesting thing that comes out of geomorphology and thinking about fluvial geomorphology is we've talked about this fact that there's alluvial rivers and there's bedrock rivers. I've said that fluvial processes sculpt landscapes, but how does water, which is pretty soft last time I checked, how does water actually sculpt the landscape? And how it's able to do that is we've got to think about, essentially, if you have sediment on the bed of the channel, as long as that bed, this surface right here, is protected and the sediment's not moving, there's no way you can get erosion of bedrock. What we have to be able to do is be able to entrain sediment, get it moving, and then you'll be able to erode the bedrock. So generally we think about this in terms of during a flood, we think about the shear stress on the bed during a large flooding event. That you're going to have a maximum shear stress at the maximum flood and then coming down the other side here. And so what we see is that the shear stress for entrainment of sediment happens for much of the flood. And so much of the time you'll be entraining the bed, but we don't have enough shear stress to actually erode the bed until peak floods. So what this means is that it's only during very large floods do we actually have enough shear stress to actually erode the bed. Now, there's also another really important variable in trying to erode bedrock. And that is the fact that you need tools to do it, because remember, water is soft. Water is softer than rock. If I just throw water at rock, I'm not going to be able to erode that rock, am I? Because water is softer. Just like when you use scratch plates in an intro lab, the feldspar is coarser than the glass, and so you can scratch the glass. But if you have gypsum or something that's softer, you can push it as hard as you want against the plate. You'll never erode it. You'll never scratch it. However, water might be soft, but it can pick up and carry things that are hard. So you need tools for erosion. And so when we think about a bedrock channel, if there's not enough tools, if there's not enough sediment, so down here on this end of the graph, so not much sediment, then your bedrock erosion rate is really low because there's no tools. Okay? However, as we increase the sediment supply to the channel, we're going to have those tools and we can get our maximum bedrock rate, erosion rate. But if we keep adding tools, we end up falling down the other side here and we actually decrease our potential for erosion. Why is that? What do you think that is? Why is it that if we add more tools, doesn't necessarily mean that we're going to have more erosion? I think you got it, right? Yeah, it's because as you start stacking up more and more tools, all of a sudden you can't move all that sediment anymore. And so that sediment ends up sitting on the base of the channel and you can't get it moving to bang into the bedrock and cause erosion. Excellent job there. All right, that's all I've got for you today. We'll be moving on to sediment transport processes in our next lecture for next time. So thank you very much for listening. Have a wonderful day and we'll see you soon. Bye.